Hello and welcome to the Algebras. In today's lecture, lecture number 7, we will talk about the Killing form. Throughout the lecture, G denotes a finite dimensional Lie algebra over a field K. For two elements x and y in G, define the scalar denoted by K of x, y as the trace of the composition of the adjoint operator associated with x and the adjoint operator associated with y. Observe that this definition produces a symmetric and bilinear form on G. Indeed, the adjoint representation is linear, so add x is linear in x, and trace is also linear in x. Therefore, K of xy is linear in x. Similarly, it is linear in y. And it is symmetric because the trace of the composition of two linear operators doesn't depend on the order of this composition. So this symmetric bilinear form is called the Killing form, named after Wilhelm Killing. A trivial example, the Killing form on the abelian Lie algebra is 0. This is because every adjoint operator associated with any element of an abelian Lie algebra is 0. Therefore, add x composition with add y is 0, and the trace of the 0 operator is 0. Here is a less trivial example. Consider the Lie algebra SL2 with respect to the standard basis f, h, and e. In this basis, the matrix of the adjoint operator of f is as follows. So it's a matrix 0 to 0, 0, 0 minus 1, 0, 0, 0. The matrix of the adjoint operator of h is diagonal with minus 2, 0, and 2 on the diagonal. And the matrix of the adjoint operator of e is as follows. So it's 0, 0, 0, 1, 0, 0, 0, minus 1, 0. So using these matrices, it is very easy to compute that the matrix of the Killing form in the same basis is given by the following. So this is a matrix where we have the second diagonal consisting of 4, 8, and 4, and all other elements are 0. We can observe that this matrix is non-degenerate whenever the characteristic of the field is different from 2. The most important property of the Killing form is that it is associative in the following sense. We claim that for any elements x, y, and z from our Lie algebra G, the value of the Killing form evaluated at the bracket of x and y and z equals the value of the Killing form evaluated at x and the bracket of y and z. Proof. Denote by x the matrix of the adjoint operator at x in some fixed basis of our algebra G. And similarly, denote by capital Y the matrix for the adjoint operator of y, and capital Z the matrix of the adjoint operator of z. Using the property of the trace, that the trace of the product of two linear operators does not depend on the order of this product, we can compute that the Killing form evaluated at the bracket of x and y and z equals the trace of the matrix x, y, z minus y, x, z. Now, in the second summand of this matrix, we can change the order of the multiplication of the operator y and xz to get xz times y. Because of this property of the trace, this does not change the trace of the outcome. So the trace of xyz minus yxz is equal to the trace of xyz minus xzy, and the latter equals the value of the Killing form evaluated at the element x and the bracket of y and z. So this proves our claim. One of the consequences from this claim is the fact that the kernel of the Killing form is an ideal of G. How do we check that? Take any element x in the kernel of K and let y be an element of G. We want to prove that the bracket of x and y belongs to the kernel of K. For this, take any element A from G and let us try to compute the value of the Killing form at the bracket of x and y and A. Using the associativity, we can move the bracket over from xy to ya to get the value of the Killing form at x and the bracket of y and a. Now the bracket of y and a is just some element in G, and x belongs to the kernel of the Killing form, therefore the second expression equals 0. And this exactly implies that the bracket of x and y belongs to the kernel of the Killing form, thus proving the corollary. Let us now discuss some further properties of the Killing form. First property assumes that we have two ideals in G with zero intersection. Then the claim is that these two ideals are orthogonal with respect to the Killing form. To prove this, consider any element x from the first ideal I, any element y from the second ideal j, and any element g from the Lie algebra. Then let us compute the image of G under first the adjoint operator for y and then the adjoint operator for x. So this is equal to the bracket of x with a bracket of y and g. We claim that this is equal to 0. Indeed, the bracket of y and g belongs to j simply because y is an element of j and j is an ideal. Therefore, the bracket of x with this element, the bracket of y and g, belongs on the one hand to I because x is an element in I. But on the other hand, it belongs to j because the bracket of y and g is an element of j. Therefore, this bracket belongs to the intersection of I and j, which is 0. This means that the linear operator add x composition with add y is a zero linear operator on G and hence has zero trace, which means that the Killing form evaluated at an element in I and an element in J equals 0. The second property, assume that I is an ideal of G. Then the orthogonal subspace of I, that is the set of all elements G in our Lie algebra, such that the Killing form of G and I is 0, is also an ideal of the Lie algebra G. So I'm trying not to say orthogonal complement because we don't know whether the Killing form is positive definite and non-degenerate, so this orthogonal subspace doesn't have to complement I. So for example, if the Killing form is identically 0, then this orthogonal subspace coincides with the whole algebra G. To prove this property, we use the associativity of the Killing form. Take any element x in I, any element y in I orthogonal, and any element g in G. So we want to prove that the bracket of G and y belongs to the orthogonal subspace of I. For this, we evaluate the Killing form at x and the bracket of g and y. Using associativity, we can move bracket to the left and get the value of the Killing form at the bracket of x and g and y. So since I is an ideal, the bracket of x and g belongs to I and y belongs to the orthogonal subspace. This implies that the value of the Killing form and these two elements equals 0, which means that the bracket of g and y belongs to the orthogonal subspace of I. Our next observation is the computation of the Killing form for nilpotent Lie algebras. Theorem. The Killing form of a finite-dimensional nilpotent Lie algebra over an algebraically closed field of characteristic 0 is identically 0. Proof. We know that all nilpotent Lie algebras are solvable. So since we work over an algebraically closed field of characteristic 0, we can apply Lie's theorem and deduce that the algebra G has a basis with respect to which each adjoint operator add x is upper triangular. At this point of the proof, not necessarily strictly upper triangular, just upper triangular. On the other hand, we also know that the adjoint operator for any element of a nilpotent Lie algebra is nilpotent. So an upper triangular matrix is nilpotent if and only if it is strictly upper triangular. This means that each adjoint operator, add x, for our Lie algebra is represented in our basis by a strictly upper triangular matrix. Now, the product of two strictly upper triangular matrices is a strictly upper triangular matrix, and the trace of a strictly upper triangular matrix is 0. Therefore, the value of the Killing form at any pair of elements of our Lie algebra is 0. Unfortunately, the converse is not always true. So here we give an example of a non-nilpotent Lie algebra which has the identically 0 Killing form. Consider the three-dimensional complex Lie algebra with bases a, x, and y, and the Lie bracket given in this basis by the following expressions. The bracket of a and x is x, the bracket of a and y is lambda y, where lambda is some fixed complex number, and the bracket of x and y is 0. It is easy to check that for any lambda, this defines a Lie algebra over complex numbers. It is also clear that each component of the lower central series of this Lie algebra contains x, simply because the commutator of a and x is equal to x. So this property means that x belongs to the derived algebra, and then when we commute with a again, we get x back, so it should belong to G2 and so on. So in particular, each component of the lower central series of G is non-zero, so G is not nilpotent for any value of lambda. Now we can compute the matrices of the adjoint operators corresponding to the basis element A, X, and Y. And these are the following matrices. The adjoint matrix of A is diagonal with 0, 1, and lambda on the diagonal. The adjoint matrix for X has -1 in the second row and first column, the rest is 0. And the matrix for the adjoint operator of Y has minus lambda in the third row and first column, and the rest is 0. Using these matrices, it is straightforward to check that the matrix of the Killing form in the same basis is as follows. So this matrix has only one potentially non-zero entry, which is the entry in the first row and the first column, and the rest is 0. The entry in the first row and the first column is 1 plus lambda squared. So this should be the square of add a and then the trace. And 1 plus lambda squared, here lambda is an arbitrary complex number. So if lambda is plus or minus the imaginary unit, 1 plus lambda squared is 0. So for these two values of lambda, we get that the Killing form for that algebra is identically 0, despite of the fact that the algebra itself is not nilpotent. So let us now formulate and prove the main theorem about the Killing form. It is called Cartan criterion for solvability of a Lie algebra. The theorem, which belongs to Elie Cartan from 1894, states that a finite-dimensional Lie algebra over an algebraically closed field of characteristic 0 is solvable if and only if the derived algebra is orthogonal to the whole algebra with respect to the Killing form. So this is an if and only if statement, and the only if part is fairly easy. So let's first prove the only if part. So if G is a solvable algebra, and since we work over an algebraically closed field of characteristic 0, we again can use Lie's theorem and find the basis of G in which the matrix of each adjoint operator, add A, is upper triangular, not necessarily strictly upper triangular. In the same basis, the matrix of each adjoint operator corresponding to the commutator of two elements is of course a commutator of two upper triangular matrices, and hence is a strictly upper triangular matrix. The product of an upper triangular and a strictly upper triangular matrix is a strictly upper triangular matrix, and hence has trace 0. This means that the value of the Killing form evaluated at an element of G and an element of the derived algebra of G is 0. So this proves the only if part of the theorem. The proof of the if part is quite complicated. In order to describe that proof, we need to do one reminder from the linear algebra. Let us remind what is a Jordan-Chevalley decomposition of a linear operator. Assume that we have an algebraically closed field K. Let V be a finite-dimensional vector space over K. Let F be a linear map from V to V. So the Jordan-Chevalley decomposition for F is the following statement. There is a unique decomposition of F as a sum of two linear operators D and N, such that the linear operator D is diagonalizable, the linear operator N is nilpotent, the linear operator D can be written as a polynomial of the operator F, the linear operator N can also be written as a polynomial evaluated at the operator F. Consequently, the linear operators D and N commute. So this decomposition holds for any linear operator on a finite dimensional vector space over an algebraically closed field. After this reminder, let us proceed with the proof of the if part of Cartan's criterion. So let us assume that the derived algebra of G is orthogonal to the whole algebra G with respect to the Killing form. Consider the set of all linear operators X in GLG such that the commutator of X and any operator in the image of the adjoint representation of G belongs to the image of the adjoint representation applied to the derived algebra. Lemma: the trace of the product of any linear operator X of our subspace X and any adjoint operator for an element in the derived algebra of G is equal to 0. Proof. So we try to compute the trace of this product. As the adjoint map is a representation of the Lie algebra, the adjoint operator for the commutator of X and Y equals to the commutator of the adjoint operator of X and the adjoint operator of Y. Using the associativity of the trace, which we established when we proved the associativity of the Killing form, we can move the commutator bracket from the right to the left in this expression and get that this trace is equal to the trace of the commutator of X with add X multiplied with the adjoint operator of Y. Now the commutator of X and add X belongs to the image of the derived algebra under the adjoint representation because of the definition of our X. The element here belongs to the image of the derived algebra under the adjoint representation. And here we have the adjoint operator for some element in G. Using the assumption that the derived algebra is orthogonal to G with respect to the Killing form, we get that this trace equals 0. So now we have to discuss the key lemma which is used in this part. Let V be a finite dimensional K-vector space and assume that we have a pair of subspaces. A is a subspace of B and this is a subspace of GLV. Define the set H as a set of all X from GLV such that the commutator of X and B belongs to A. Assume that X is an element of H such that the trace of X times Y is 0 for any element Y in H. The claim of the lemma is that such X is nilpotent. Let's try to prove it. Consider the Jordan-Chevalley decomposition for X. X is equal to D plus N. D is diagonalizable. N is nilpotent. D is a polynomial in X. N is a polynomial in X. D and N commute. So this induces the Jordan-Chevalley decomposition for the adjoint linear operator of X. So the adjoint linear operator of X is given as a sum of the adjoint linear operator of D plus the adjoint linear operator of N. Again, add D is semi-simple, add N is nilpotent, and they both are polynomials in add X and commute. Moreover, we can also observe that if we write D as a polynomial in X and then compute add D as a polynomial in add X, the contribution of the constant term of the polynomial D as a polynomial in X is 0 because the constant term commutes with any linear operator. This means that we can write add D as the polynomial in add X, where our polynomial does not have a constant term. But from this, it follows that the operator D, when commuted with any element in B, gives an element in H, simply because F is just a linear combination of X, X squared, and so on, and of course X and X squared and so on, they all have this property. So this implies that D is an element of our set H. So we also know that D is diagonalizable, so let's fix some eigenbases for D, consisting of vectors EI, where I runs through some index set I, and let AI be the corresponding eigenvalues. What we want to prove that X is nilpotent, which means that we want to prove that D is 0. In other words, we want to prove that all AIs are 0. Define E as the vector space over rational numbers spent inside the field K by all AIs. We want to prove that this vector space is zero, and we will prove it by proving that any Q linear map from this vector space to Q is the zero map. Define a linear operator Z from V to V in the following way. The same basis is an eigenbasis, and the corresponding eigenvalues are given by the values of phi of AI, where phi is our fixed linear map from E to Q. So we want to prove that phi is zero. So since we have fixed basis in V, we have a natural basis in GLV consisting of, so to say, matrix units Eij, which is induced by EI. So Eij is the linear operator of rank 1, which maps Ej to Ei. This is an element of GLV. In this basis, it is easy to check that the commutator of D with Eij is equal to Eij times Ai minus Aj. And the same computation shows that the commutator of Z with Eij is also equal to Eij times now phi of Ai minus phi of Aj. Since phi is a linear map, we can rewrite it as phi of Ai minus Aj times Eij. So the adjoint operator of Z is diagonalizable in this basis with diagonal elements given by phi of Ai minus Aj. Now we can find a polynomial r of x without constant term such that for all I and j, the value of this polynomial at Ai minus Aj is equal to phi of Ai minus Aj. So we have a finite number of points at which we prescribe the value, and this can certainly be satisfied by some polynomial. Then we can write the adjoint operator of Z as this polynomial R evaluated at the adjoint operator of D by definition. In particular, this implies that Z is an element in H. Our assumption that the trace of x times z is equal to 0 can now be rewritten as a sum over all I. Ai is the eigenvalue for D, so it's the diagonal element of x, times phi of Ai. Phi of Ai is the eigenvalue for z. Applying the linear map phi, and using that it is linear over rational numbers, and phi of Ai is a rational number, it can be moved out, this becomes the sum over I, phi of Ai squared, is 0. But this is now an equality for rational numbers. If the sum of squares of rational numbers is 0, then each of the numbers must be 0. So since all phi of Ai's are rational, we deduce that each phi of Ai is 0, and therefore phi must be the 0 map. And as we said last time, so we had a vector space over Q, and we proved that any linear map from this vector space to Q is 0. This means that this is a 0 vector space. In particular, it means that all AIs are zeros, which means that D is the 0 operator, and hence X is nilpotent. Now we can complete the proof of Cartan's criterion. We apply our lemma to the situation where we have GL of G with two subspaces, the image of G under the adjoint representation and the image of the derived algebra under the adjoint representation of G. So applying the lemma, we conclude that the image of the derived algebra under the adjoint representation of G consists of nilpotent linear transformations. Recall that we have proved that the trace of the product of each element x from this space with the adjoint operator related to any element of the derived algebra is 0. Therefore, using lemma, we deduce that the image of the derived algebra under the adjoint representation of G consists of nilpotent linear transformations. Using Engel's theorem, we now can deduce that the image under the adjoint representation of G of the derived algebra of G is a nilpotent Lie algebra. So this algebra is obtained from the derived algebra by factoring out a part of the center. Since any Lie algebra is nilpotent if and only if its quotient by the center is nilpotent, we can deduce from this that the derived Lie algebra of G is a nilpotent Lie algebra. But this implies implies that the algebra G is solvable. Under our assumptions, an algebra is solvable if and only if the derived algebra is nilpotent. So this implies that G is solvable and completes the proof of Cartan's criteria. Thank you very much. Hope you enjoyed the lecture.